And now let's welcome Chao from Ethereum Foundation with the workshop MACI and Quadratic Funding. Welcome on stage.
Hello? Yeah, so today I will talk about the MACI and its application on the quadratic funding. My talk consists of two parts. The first part is about the introduction to the MACI and its background. The second part is one of the major applications of the MACI, which is called the quadratic funding. So the MACI stands for the Minimal Anti-Collusion Infrastructure. The idea is originally proposed by Vitalik, and then has lead research by Barry and Kobe. Then it's developed by a million developers. So the major issue the MACI want to solve is the bribery issue. So suppose we have some online elections. Let's say a user want to vote for some multiple options. And how can we avoid the user just bribe offline? So which means, for example, the Alice can pay the Bob for some money and buy Bob's key to vote for Alex's preference. So this kind of attack is something we want to avoid. So the basic idea is we just encrypt every message. After the encryption, you can imagine all of the message just looks like a random string. So from the outside point of view, you have no idea what is the content of this message. And also, we will allow the user to change his voting key. So this is also important. I will explain later. And after the encryption, how do we guarantee the message is processed correctly and the final tally result is computed correctly? So this is done by the zero knowledge proof. It can guarantee us all the computation is done correctly. And the major applications like Clear.fund and QFI, they are all existing projects on the quadratic funding and utilize MACI as the underlying infrastructure. And here is the original article from the Vitalik. So the solution is like this. There are basically two stages. The first stage is some kind of KYC process, and all the users just register your voting key on some register smart contract, and you can use whatever the KYC or like whitelist, whatever method you want. So this is done by once. After the sign up is finished, the next stage is just the voting. So we can have multiple voting period. And when the user votes, he will just encrypt his voting message by the coordinator's public key. I will explain what is the coordinator means. So basically, you can imagine this process looks like you encrypt your message and send to the voting smart contract. So this is what is a valid message here, but it's just some technical detail. You can just ignore it. So we'll explain why with this way the Alice cannot bribe Bob. So here is the Bob strategy. During the sign up, Bob is sign up with his voting key, and during the voting period, Bob will vote for some options. Then Bob can send another message to just change his voting key. So after he changes his voting key during the poll process, he can just vote with his new key, and all his voting will just override the previous vote. It means the previous vote will become invalid. The system will only accept the latest key with the latest vote. So in this case, let's say the Bob first vote for some message and change his key to a new key, and vote for another message with a new key. So from Alice's point of view, Alice has no way to know Bob has ever changed his key or not, because all the message is encrypted, and Bob cannot prove it. He didn't send such things. So this basically breaks the trust between bribery and bribery. So this is how the MACI can stop the bribery. So of course, in this case, Bob can still give Alice the correct key, but Bob cannot prove it. So basically, their trust is just no longer exist. So as I just explained, the trust coordinator is some third-party trusted party who is responsible to just process all the voting message. So here I list what they can do and what they cannot do. So the first thing they can do is they can decrypt all the messages to some valid command or invalid commands, if the user send an invalid message, for example, we just encrypted by another key or just do arbitrary random message, the coordinator can still make a proof to show this message is invalid and just silently ignore it when you do the tally. So basically, this is what the coordinator can do. Of course, the coordinator can also withhold all the processing. So which means the coordinator can just stop the liveness of the system. And another more serious issue is we have trusted the coordinator will not collude with the bribers, because the coordinator has the power to decrypt all the messages. So if they collude with the briber, it means the briber can know which message is from who and who changes the key. So this is definitely the trust assumption we have to assume. What the trust coordinator cannot do, he cannot censor the message, because all the voting message is sent through a smart contract, and he has no way to stop people sending the message to a smart contract. So he cannot censor it. And also, he cannot compute the message or tally result incorrectly. This is guaranteed by the zero knowledge proof and by a smart contract. So here, a smart contract is trying to ensure the correct order of the message. So the coordinator will not just ignore some of the message. So basically, the smart contract allows the coordinator process the message one by one with the correct order. And the zero knowledge proof just guarantee the coordinator cannot fake the proof or fake the computation. So here is the basic architecture design in the right picture. You can just ignore it. And the left side is the workflow. So basically, there are two stages. The first stage is the sign up stage, and the user will just sign up in the sign up stage for their voting key. This can be done once. And the second stage is the voting. So for example, it can be multiple rounds. For example, in the round 1 for this week, we are voting for some 10 projects. And the next week, it's a new round. We are voting for a new, let's say, 20 project. So basically, this is how the workflow of the MACI goes. So after each of the voting period, there is the first phase is voting. So after the voting deadline passed, it's time for the coordinator to process all the messages. So because of ZKP, he will process all the message and create a proof. After the proof is created, he will submit the proof to the on-chain verifier. And the on-chain verifier will verify everything is correctly. And if everything is correctly, the on-chain verifier will update the latest status and the final tally result, the commitment of the tally result. So basically, this is how the MACI workflow going. And the next part I'm talking about the quadratic funding. So basically, from the traditional funding, when the donor just voting for one key, he basically contributes $1 for it. And if the donor want to vote for 3 keys, he just contributes $3. So this is how the traditional funding goes. And for the quadratic funding, it's slightly different. So imagine one user, like in this picture, one user donor just donate one ticket, which means he contributes $1. And another user, he votes for 3 tickets. In this case, he has to contribute 3 square, which is $9. So this is why we call the quadratic funding. So basically, it means the marginal interest you strongly want to vote for something is proportional to the amount, the marginal cost you have to pay, and this will make everything quadratic. So like this example, in the square, the bottom one, the big square is whatever the final funding the project will accept. And you can see the green box is the matching pool. So basically, we will also have a matching pool. We'll match whatever the donors contribute, basically make it a square. So in this case, one donor, 1 ticket, the other donor, 3 tickets. So the total is 4 tickets. And we'll match in the $6 to make it as a 4 square, which is $16. So this is a normal quadratic funding, the mechanism. But this is some issues, some attacking factors. For example, there are 2 cases. The first case is still 2 donors, as before. One donor votes for 1 ticket, and the other donor votes for 3 tickets. So total 4 tickets. So the matching pool will match $6. And in the second cases, there are still 2 donors. One donor will vote for 2 tickets, and he pays $4. And the other donor also vote for 2 tickets, he pays $4. So in this case, the matching pool will match $8, still 4 tickets, $16. As you can see, in this case, will extract more money from the public funding. So there's a kind of attack. Let's say two users collude with each other, but we just support our project behind. So we contribute our own money to this project, and we just contribute, each of us contribute a large amount of money. So this can extract a large amount of money from the public good. So this is some kind of attack we try to avoid or try to minimize their risk. And the idea is also proposed by Vitalik in this post, which he called the pairwise coordination subsidy. So intuitively, if you say, look at the box, the green square is the individual contribution from all the individual donors, and the area is what the individual contribution, how much dollar he contributes, and the side length is the ticket, and the area is the contribution of the dollars, and all of the yellow rectangle is the matching from the public fund to this, so make it a square. So that's what I just explained, the normal quadratic voting, quadratic funding. So the idea, as you can see, like these two, green square, their contribution, their correlation is kind of large. So their corresponding the yellow triangle is a large area. They will extract more money from it. So the idea is simple. We just multiply a scaling factor on each of the small rectangle. So the final contribution from the public funding is the area of the rectangle times the scaling factor. So for example, in this biggest yellow rectangle, we times the smaller scaling factor. That is the amount of the contribution from the public pool. And if you with the area times the scaling factor added together is whatever the public funding will match for this specific project. Of course, the number here is I just make it up, give you some intuition. The actual formula is different, and we can prove with the actual formula. There's a maximum upper bound the malicious user can extract from the public funding. And the next slide is just on technical detail if you are interested. So the first thing is, as we know from the zero knowledge proof, everything happens in the finite field. You can imagine this is a big integer, modulus on some prime number. So basically, this is how the numbers were treated with, the integers kind of. But in the correlation, when we calculate the correlation from two donors, actually is a float point, like 0.1, 0.3, 0.5. So we first thing is we have to emulate the float number by the integers. So the idea is simple. For example, the integer 1, 2, 3, 4, 5, and if we use the last 3 digits to represent the float, and the first 2 digits to represent the integer part. So 1, 2, 3, 4, 5 means 12.345. So with this analogy, here are some rules for division, multiplication, and addition, subtraction. For example, for division, we will divide 1 over 2. If first times 1,000 divided by 2, you get 500. So 500 in our analogy is just 0.5. So this is how we do the emulation for the float number. And secondly, something I learned when I developed the Circon. Here we are using Circon programming language. Basically, the Circon compiler cannot allow user to put the input signal. It's kind of like a variable input signal in any expression, control flow, array size, or array index. So this is, you can imagine when you do any hardware circuit design, you have to know the circuit shape and the circuit size before you are actually running. So basically, you have to know everything, the shape of the circuit at compiler time. So in this case, for example, when we treat the integer division, we will have to choose the division algorithm with a fixed maximum bit length to avoid any unknown signals. And also, when we do the correlation coefficient, for example, we have the 4 users, U1, U2, U3, U4, they try to voting, and their corresponding correlation as 6, 1, like C12, C13 until C34. So one way is to, let's say you have a bunch of users, we have to treat this long correlation array by batch, because we have the upper limit for treat the upper bound of how many messages we can process. So when you treat everything in a batch, if you first, of course, for batch size, we can fix it. For example, each batch is 100 message or 100 users. That's fine. But for the when you try to indicate a batch, you have to indicate the index, start index of the batch and the batch size. But if we are trying to mapping from the coefficient array to the user array, basically from the right side, C1 to C34 to the right side, from 1D array to a 2D array, this mapping is kind of irregular, and you cannot avoid the compiler error to avoid the start index appear in the either for loop or appear in the array index. So instead, we just doing the other direction. We do the mapping from the user pair, like a UI UJ, to the correlation matrix, 1D matrix. So correlation 1D array. So in this case, we just assuming there are four, in this case, 4 users, U1, U2, U3, U4, and we have 2 batches. So in reality, of course, you have a large user base and several batches. And each user batch, you can imagine, is a subtree of the Merkle tree for the users. And we can hash each batch to get an upper leaf node, which is kind of the leaf node of the Merkle tree. And we just, for each batch, we provide the Merkle proof with the hash of the batch. So in this case, we can avoid this unknown like an input signal in some expression or like for loop or in the array index size. And this is the illustration. So basically, when you calculate it, it's a correlation matrix. You can calculate it for each batch, like a B1 to B1, B1 to B2, or B2 to B1, B2 to B2. So this is how we deal with this kind of scenarios. So this last 2 slides just some lesson I learned. So thank you. So that's all from today's talk. If you have a question, just let me know.
How do you, when you do KYC to users, how do you protect their privacy? Like if they have to do KYC?
Yeah, so for the KYC part, so actually this is not the design of the MACI. We make it just a separate component. So basically, whoever runs this programming, they will design your sign up or KYC process, either whitelisting or just probably you have to check it and don't record the identity. So this part is, I would say, not the infrastructure missing. We just make it modularized. So you can plug in and with different kind of KYC process or the sign up process. We are mostly focused on the second stage, basically the voting tally. Yeah.
I still don't understand. How do you, so the data of the user, where is it stored?
So the data of the user will store. So currently in our demo, actually from MACI point of view, the user's data is stored in the sign-up contract or the MACI contract. So basically, when you do the KYC, you just register your voting key. It's kind of the public key, but it's different from the Ethereum key, and also with the balance, initial balance. So basically, it's a hash of the initial balance and the public key into the Merkle tree.
Gotcha. Thank you. And also for the correlation between users when you solve, so when you solve the pairwise coordination subsidy, when you calculate the correlations between the 2 users, can you explain that again?
What's your last sentence?
So like I don't understand, like how do you calculate the correlation?
Oh, how to calculate correlation, right?
Yeah.
So basically, for example, for this project, this user votes for V1, this user votes for V2, so V1 plus V2 times together, so for one project. And if at the same time we have multiple projects, for each 2 users, we will calculate the contribution of their pair for each of the project added together, we get some number, and then we use some protocol constant m, capital M over M plus that number. So basically make it between 0 and 1. And you can check this, I should get some barcode, but That is, if you search for the pairwise coordination subsidy and with Quadratic keywords, you can see the exact formula.
Gotcha. Thank you.
Yeah, no problem.
Previously, when you try to handle the floating point number, is it the fractional numbers?
Could you repeat the question?
When you try to handle the float numbers, is it the fractional numbers?
Oh yeah, you mean the number here, right?
Yes.
Yeah, it's a floating number, but I will fix some, let's say, 4-digit size. So basically, the accuracy is up to 4 digits.
I see. And is it possible for the sign,
A sign, right?
the sign bit?
Oh, so here, because everything is positive, and the correlation is, coefficient is positive, so we don't need to worry about sign bit.
Thanks.
Any other questions? I think that's pretty much it. Thank you, Chao Ma.